Hello students, once again welcome to the LJ Institute of Engineering and Technology. Let's start with the course Mathematics 1 and the chapter is partial derivatives. Today's topic is partial derivative of homogeneous function, part 1. As we have seen what is homogeneous function and how we can find or how we can check the given function is homogeneous, and if it is homogeneous then what is the degree of function we have seen in previous lecture. We will use that concept in this topic, okay, and this topic is divided into two parts. So let's start with the first part, part 1, and in this part first we will see the Eulers theorem on homogeneous function. So first, what is the statement of Eulers theorem on homogeneous function? That means if given function is homogeneous, then and only then we can apply this Eulers theorem. So let's have a look on this statement. If u is a homogeneous function of x and y of degree n, then x del u by del x plus y del u by del y is equal to n into u. That means given function is homogeneous with degree n, then we can apply this concept. That means if you want to find the value of this x del u by del x plus y del u by del y, then you can use directly n into u. N is a degree and u is a given function. You can write directly. So whenever example is given, you have to just check when this format is given in proof. Okay, when this part is given in the proof, then you have to just check that given function is homogeneous, and if it is homogeneous, then you can write down answer directly degree into given function. Now, before starting example, we have to check or we have to prove this theorem. So let's start with the theorem proof. Since u is equal to f of x comma y is homogeneous function of degree n, because it is given in the statement that u is homogeneous function of x and y and with degree n. So we can write this u in the form of x raised to n into phi of y by x. How this term we have seen in previous lecture, that means in topic homogeneous function. Okay, by taking x raised to n common, new function from this will be phi of y by x. Say equation number 1. Now by differentiating this u with respect to x one time, then multiply by x, and differentiating with respect to y partially and multiplying by y, by adding these two terms we will get this answer. Okay, so by differentiating equation 1 partially with respect to x, we have u becomes del u by del x, and here we are differentiating partially with respect to x, and x is in both terms, x raised to n and in this phi. So we will apply product rule here. And what is product rule? We know that this term, any of this term is as it is, that phi is as it is, and differentiation of x raised to n is n into x raised to n minus 1 plus, now x raised to n is as it is, and differentiation of phi of y by x. So differentiation of phi is phi dash of y by x into, by chain rule, differentiation of y by x. Now differentiation of y by x, we are differentiated with respect to x partially. So differentiation of y by x partially with respect to x, so y constant. So we have 1 by x, and differentiation of 1 by x minus 1 by x square. So we have minus y by x square. Okay, this is here. Now by simplifying, we have to multiply this term with here. Okay, so we have this term as it is, and plus minus minus x raised to n, and this is x square, so it will be x raised to n minus 2, and y as it is, and phi dash of y by x as it is. Now we multiply this term with x. So we have x multiply here, x multiply in this term, x multiply in this term. So if you multiply x here, so x raised to n minus 1 into x, so x become n and x into x raised to n minus 2, that means x raised to n minus 1. Say equation number 2. Same way we differentiate equation 1 partially with respect to y, and then we multiply with y. So differentiating equation 1 partially with respect to y, so we have del u by del y is equal to, this time this x raised to n is constant, so as it is, and differentiation of phi of y by x is phi dash of y by x into chain rule, that means differentiation of y by x is 1 by x, because we are differentiating with respect to y, so differentiation of y is 1 and x as it is. Now by simplifying this x and x raised to n, we combine, so become x raised to n minus 1 and phi of y by x as it is. Now we multiply this term by y, so y and y. Say equation number 3. Now from equation number 2 and 3 we will add x del u by del x plus y del u by del y. So we have this answer for x del u by del x and this for y del u by del y from equation number 3. So here you can see that this entire term, these both are same, so cancel out because plus minus sign. So we have remaining term x into x raised to n into phi of y by x, and you can see that this is our given function u. So we have this x del u by del x plus y del u by del y is equal to n into u, and this will be happened if given function, this u is homogeneous function with degree n. So we will get answer n into u. Okay, for that you have to first check given function is homogeneous, and hence it is proved. Okay, this is the proof of Eulers theorem, okay, on homogeneous function. Now we have two corollary. And what is the corollary? Let's have a look. And before corollary, we have the generalization of the Eulers theorem. That means we can apply Euler theorem for more than two variable. That means u is a homogeneous function of kth variable, that means x1, x2, x3, x4 up to k variables of degree n. Then we can apply Euler's theorem x1 del u by del x1 plus x2 del u by del x2 plus x3 del u by del x3 plus xk del u by del xk up to so on, matlab to k is equal to n into k. That means answer is always degree into given function, but for that given function should be homogeneous with a degree, some degree. And whenever this format is given, then we will check homogeneous, and it is homogeneous, then we can write directly answer. No need to differentiate. Okay, but we have differentiate in theorem because we want to prove that theorem, that's why. But in example, no need to find it all these derivative, no need. Okay, now this is corollary. That means for second degree derivative, second order derivative. So if u is homogeneous function of x and y of degree n, then x square del square u by del x square plus 2xy del square u by del x del y plus y square del square u by del y square is equal to n into n minus 1 into u. So if u is homogeneous function, we have applied for one order, same way we can apply for the second order derivative, but for that we have to remember this term, that is this format. So whenever in example, if this format is given on the left hand side and given function is homogeneous, then you can use this statement directly. No need to find all these differentiation derivatives. Okay, you can use directly this Euler's theorem. Okay, so to understand better Euler's theorem, let's have a look on the example. First example, verify Euler's theorem for the function u is equal to this. What is the meaning of verify? So first we will apply Euler's theorem, and whatever we will get the answer, we verify by differentiating given function, because it is asked here, verify. If verified word is not given, then we can apply directly Euler's theorem, and this is our final answer. But here verified word is given, so we have to verify that Euler's theorem by differentiate given function. So let's start with the solution so we can understand how we will apply this step. First start with the given function u, and as I told, to apply Euler's theorem, we have to check given function is homogeneous or not. And how we will check the given function is homogeneous or not, we have seen in previous lecture. That means we will put x is equal to tx, y is equal to ty, and z is equal to tz in given function. So we have dx, dy, tz here, and x square, y square, z square become t square x square, t square y square, t square z square, whole raised to minus 1 by 2 as it is. Now if we take t square common, so power is also common with the t square, so power will be minus 1 by 2. At 2 cancel out, we have t raised to minus 1. So t2 cancel out and we have t raised to minus 1, and this is our given function u of x comma y comma z. So this is the definition of homogeneous function. So we can say that u is homogeneous function with degree n is equal to minus 1. Okay, so given function is homogeneous, so we can apply Euler's theorem, Euler's theorem, we can say Euler's theorem, x del u by del x plus y del u by del y plus z del u by del z is equal to n into u. And what is n? N is minus 1, so minus u. This is our final answer of given question. But here one word is given verify. So now we have to verify this step. That means by differentiating given function with respect to x, with respect to y, with respect to z, then after multiplying x, y and z, by adding this, if we will get minus u, then Euler's theorem is verified. And if we did not, we don't get this minus 1, then we are wrong here. Okay, but as we have seen, if given function is homogeneous, then Euler's theorem is always applicable, and just we have to here verified only. This is the only one process because it is mentioned in question, that's why. So let's start with the u. So here u is given, and we will differentiate this function, okay, with respect to x, then multiply by x, with respect to y, then multiply by y, with respect to z, then multiply by z, and by adding this we will get minus u. Okay, let's have a look on the process. So we have differentiating with respect to x, so this term whole raised to minus 1 by 2, so we will apply power rule, minus 1 by 2 forward, 1 power minus, and differentiation of base is x square's derivative is 2x, and differentiation of y square and z square is 0. So by cancel out this 2, we have minus x into this. Now multiplying with x, we have x into x becomes x square. So it is equation number 2. Similarly, we can find differentiating with respect to y partially by cancel out this 2, and by multiplying by y, we have equation number 3. Same way, we can differentiate with respect to z, and by cancel out this 2, we have this term, and by multiplying with z, we have this equation number 4. By adding equation number 2, 3 and 4, we have this equation 2, this is 3 and this is 4. We can take common minus 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 in this bracket. So in remaining bracket we have x square plus y square plus z square. Why plus? Because we have taken minus common, that's why. And base same, so addition of power minus 3 by 2 plus 1, so we'll get this, and we know this is our given function u, so we have minus u, and hence Euler's theorem is verified. Okay, so this step is you have to apply when verified is what is there. Verify Euler's theorem, then otherwise no need. So one more example without verify. Let's have a look on the example. If z is equal to x into y f of y by x, and so that x del z by del x plus y del z by del y is equal to 2z. In this example, there is no any word mentioned here, Euler's theorem. So how we understood that this example is from Euler's theorem? You have to see this, you have to observe this left hand side. If left hand side is the statement of our Euler's theorem, then you have to check homogeneous function, and if the given function is homogeneous, then we can apply directly Euler's theorem. Okay, so let's start with the this given function, and as I told, to check homogeneous function, z is written as z of x comma y. So by putting x is equal to tx, y is equal to ty, we have this xy become tx comma ty, this x is tx, y is ty, this y is ty, and x is tx. By cancel out t, by combine this t, we have t square and this function, and you can see this is our entire z of x comma y. So this is the definition of homogeneous function. So z is homogeneous function with degree n is equal to 2. It is clear, we can see. Now it is homogeneous function with some degree, so you can apply Euler's theorem. And what is Euler's theorem? X del z by del x. Here I am using z because given function is z, that's why. So z is homogeneous function, and that's why by Euler's theorem, x del z by del x plus y del z by del y is equal to n into z, and n is 2. So by putting here 2, we have the answer to z. So easy. Okay, so this kind of example is very easy. You can do by yourself. Any example you can do, but there is a one question in your mind, sir, if this function is not homogeneous, like you just taught us in previous lecture, that one last example is not homogeneous because of that t square stuck within tan inverse. So at that time, what we should do? So at that time, you have to apply modified Euler's theorem, and we will see modified Euler's theorem in next lecture, that means in part 2. Before that, you have to do this practice example. This is DIY, do it yourself, and if you practice this example, you can understand next lecture better. So keep practicing. Thank you for watching this video. We will see you soon with the next lecture. Thank you very much.